Hi, in this video we're going to take a look at backtracking, which is a common paradigm to solve many algorithmic problems, and then we're going to see how it can be applied to answer these questions on LeetCode at the following link. To see how backtracking works, let's look at the first question that we can solve using backtracking, which is called combinations. In this problem, our program has input received two values, n and k is an integer less than n, and our program should receive these values and return all possible combinations of k chosen from the range 1 to n. So you're probably familiar with the concept of combinations in probability theory, but I'm going to give a quick recap of what it means. As an example, let's say we have 9 people labeled as 1, 2, 3, etc. all the way to 9. And also we have 3 chairs. And the question asks us to return the ways that we can seat these people on these 3 chairs such that the order doesn't matter. What it means is that, for example, if we choose the first person to sit on the first chair, the second person to sit on the second chair, and the third person on the third chair, this is one way to arrange the 3 people out of 9 on these 3 chairs. But another combination of these people on these 3 chairs, for example, if we seat the second person on the first chair, first person on the second chair, and third person on the third chair, and this arrangement should not be counted as another way to seat the people labeled as 1, 2, and 3 on these 3 chairs. So to see how backtracking works in this example, let's say we have an empty array sitting at the root of a tree. Let's say we have n as 4 and k as 2. So initially we can choose any number between 1 to 4. So this is the first layer of this tree, and let's say we chose 1. So the other options that we can choose are 2, 3, or 4. So what we can see here is that we have a list which has a size of 2, which is the same number as k that we initially wanted, because we wanted to choose 2 from 1 to 4. So this is one answer in our final result. And similarly, 1, 3 and 1, 4, these lists also they have the size 2, and these are 2 other solutions to our problem. But let's move on and see if we choose 2 as the first element in our list. So let's say instead of choosing 1 first, we choose 2 first, and the other options that we can have after choosing 2 first are 3 or 4. And the reason for that is that if we choose any value less than 2, let's say 1, it would give us the same result if we had chosen 1 first and then 2, which is an answer we don't want. So in this level, our lists, they have also the size of 2, which are correct answers to our problem. And then we can continue. For 3, we have only one other option that we can choose. And for 4, we don't have any other options. So let's see how we can write a Python program that fills the list as if it was following this tree-like execution. So let's first define a list called res, which should contain eventually all of the leaves of the tree that I showed you on the paint app. And let's return the result. So here I will call a function which I'll define shortly. So this function, which will call itself recursively. So the first argument is self because it is defined in class. Then res in k and a temporary variable, and the parameter that we'll call current iteration. So as the base case of this function, it checks whether the length of temp is equal to k. If that's the case, it will append that list to our results list, and then let's return. Here the temp list refers to this list that gets filled as the program executes. So if it's not the case, then length of temp is not equal to k, which is the case that we arrive at the leaves of this tree for our current iter, which is the current iteration, which initially is 0 when we call the function, 2n it appends that number which starts from the current iteration to the temp list, and then recursively calls itself, passing all the parameters, and then it just pops the last elements of temp. So if you run the program, you should return the correct solution. So this example shows how a general solution for a backtracking problem works. So a few things I noticed here is that it's a recursive structure, so the function calls itself. Then there are a couple of state variables that at each iteration they can get updated. For example, res is a list that will contain all the results. N and k can get updated for each different iteration, which in this case they will stay fixed. But temp gets updated in each call, and I+1 also gets updated in each call. So in this tree, at each execution run, we can think of a combination of states that at each iteration they will have a value. So for example, the res list initially is empty, and n and k, they initially have values that depending on input, let's say they are n and k. Then temp is this list that I will also put here, and then current iteration here initially is 0. So as we move down this tree and the function basically calls itself, each of these values can get updated. So now I will show you the general structure of a backtracking algorithm, which has the following form. So here we have a function called backtrack, which calls itself here. So initially we call the backtrack function and we pass an empty state. The backtrack function receives the state, and if the state is valid, it appends that to answers list, which in our case was the res list. And this is basically the base case of the recursive function. And here for all candidates in get candidate state, we append the value to the state list, then we backtrack, and then we remove the element that was added before backtrack from the list. The combination sum problem is very similar to the combinations problem we saw earlier. Here we have a set of candidates, let's say 2, 3, 6, 7, and also we have target value, which can be, for example, 7. Then the program should return all combinations of the candidates such that the values in the combination should add to the target value. But one thing that I notice here is that we can use a candidate unlimited number of times. So 2, 2, 3 is also a valid combination, even though 2 was repeated 2 times. Here we have additional parameters. The first one is candidates, which is a list of values which correspond to our candidates that was given as input. Then we have a target value, a temporary, which was as before, it's the temporary list which gets updated in each iteration. And also we keep track of current iteration, which is the same as what we had before. As a base case, we check if the target value is 0, and if so, we append our temporary list to our results list. And if it's not the case, we make a for loop from current iteration to the length of the candidates. So first thing we check here is that if the candidate has a bigger value than target. If that's not the case, we append the candidate to the temporary variable. Then we subtract the value of the candidate from the target, and then we pass temporary and I. And notice here we don't pass I+1 but I, because we want to allow unlimited number of times that each candidate can be used. Then lastly, we pop the element from the temporary variable. So this algorithm shows one important aspect of backtracking algorithms, and that is while we are branching out, we don't blindly follow a for loop. For example, in our initial example, we iterated from the current iteration, which for example here was 2, until the value of n, which for example was 4, and then we just add those values to the temporary list, and then we call the function itself. But as we can see here, we can be smart about it. So for example, we can check if the value of the candidates is larger than target, then we just don't bother with branching out. So the point here is that the for loop can contain different set of code to check, for example, different conditions, and if the conditions are not met, we just don't bother with branching out from that node. So this problem is perhaps easier than the previous one. So as input, we are given a number of digits, for example, numbers 2 and 3, and we are asked to return all the possible combinations that we can get by pressing these two numbers on the old dials that we had on the old phones. So one way to solve this is define a dictionary that maps each digit to their corresponding letters. For example, 2 gets mapped to ABC, 3 to DEF, etc. Then we pass the dictionary alongside the other parameters to our function. Then for each letter that we get from mapping the digit to their corresponding letters, we first add the letter to the temp variable, which is of type string. Then we call the function itself and pass res all the digits except the one that we are processing, the same map that we initially had, and also the value of the temp that we just updated. So here you can see if temp is not a list and of type string, you can subtract the element using this syntax. Then for the base case, we should check if the length of the digits are 0. If it is 0, we just append the temporary string that we created to the result and then just return from the function. So the next question that we want to take a look at is called generate parentheses. So as an input, it receives an integer, for example, it can be 3, and the program should return all the value combination of parentheses for a given number of parentheses, for example, 3. So let's first see the execution history of the program that solves this problem. So initially we start with the empty list, which doesn't have any parentheses in it. Then here we only have one choice, and that choice is to add the opening parentheses. And here we get two choices. Either we can close the parentheses or open another parentheses. Here we only have one choice, and that one is to open another parentheses. But here we have two choices. We can either close the parentheses or open another one. So as we can see here, in each execution step, we should know the number of opening and closing parentheses that we had so far. And to keep track of that, I define two variables. The first one I will call C, which keeps track of the number of closing parentheses that we had so far. And initially it has a value of 0. And the next variable I call O, which keeps track of the number of open parentheses, which is also initially 0. On the first iteration, the number of closing will still remain 0, but number of opening parentheses will change to 1. And at this step, we check if the number of opening parentheses is bigger than number of closing parentheses. We can close the parentheses by adding a closing parenthesis to the list. And for the opening parentheses, we only check if that number is less than the maximum number of parentheses that we want. For example, it can be 3. And if that's the case, then we add another open parenthesis. And for the base case, the number of elements in the list will be twice as much as the number of open parentheses, because we have as much closing parentheses as we have open parentheses. So for this case, it will be 6. For example, it is this combination. As I mentioned, we need two variables to keep track of number of opening parentheses and number of closing parentheses, and these are represented using these two variables. And for the base case, the length of the temporary variable equals to the twice of number of opening parentheses that we had. We append the temporary variable to our final result, and then we return. And if the number of opening parentheses is bigger than the number of closing parentheses, we add another closing parenthesis, and we call the function itself, but we increase the number of closing parentheses by 1, and afterwards we just remove that closing parenthesis. And for our case, we just check if the number of opening parentheses is less than the total number of open parentheses that we can have. One thing to notice here is that we don't necessarily have to have a for loop. Here we can have two different ways to branch out for a given function execution, and those two ways were made possible by two if statements. So the last problem that I'm going to talk about is called n queens, and the problem is that for an n by n board and n number of queens, what are the number of possible ways that we can place these queens such that no queens are attacking each other? So if you're comfortable by thinking how the solution might work in terms of a true execution, then the solution becomes pretty easy. So we start from the first row and we place the queen on the first column of the first row. Then we check if that's a valid move by checking if no other queen in the board is attacking that queen. And if that's the case, we proceed by going to the second row, and on the second row we do the same thing. Since that's not a valid move and the first queen that we had placed on the first row of the first column can attack that queen, then we move to the second column. And since that's not a valid either because the first queen can diagonally attack our queen, we go to the third column. This is a valid location to place the queen, so we place it here, and then we go to row 3, and then we repeat this process. And if we can reach to the last row, and that means that we could place all the queens on the board without order of 2 of them attacking each other. And the code for this problem is pretty straightforward. We first check if the number of queens that we could place on the board matches the number of rows of the board, and if that's the case, we append a temporary variable, which in this case is the configuration of the queens on the board, to the res list. And if that's not the case, we loop for each column in the board, then we place a queen. We check if that's a valid move. If that's the case, we recursively call the function, and either case we remove that queen from the board. Thank you for watching. I hope this video was useful for you, and see you in the next one.